So finishing up the last unit of study, which was the solution state, we're going to start moving into a couple of units of study which circle back and look at the physical states themselves, solids, liquids, and gases. We're going to start with the gaseous state. So this entire Unit 11 has to do with gases, and we're going to look at this from beginning with more of a descriptive sense, definitional sense, and then we'll get into what are called gas laws, where we'll take a more calculational turn. As we discussed before, when looking at the different phases of matter, it is important to analyze them on the particulate level with respect to their particles. Now, gases, the gaseous state, stands alone with respect to the fact that the particles of a gas are never in constant contact, or never in contact. Particles of liquids and solids are always in constant contact with other particles, but here gases stand alone. And as such, gases can thus be described by what is known as kinetic molecular theory, which has four basic tenets. The first is that it's a collection of particles in constant motion. You can see in the picture over on the left, the little zip lines behind those little spheres there are meant to be the particles of the gas, and they are always moving. They're never stationary. Also, it is assumed, this isn't always the case, but it is assumed that there are no attractions or repulsions between the particles. And when they do collide, like we see in this model right here, they collide in a fully elastic fashion, sort of like billiard ball collisions. Now, the diagram over on the left-hand side does not do justice to this to the kinetic molecular theory, because in reality there is a lot of space between the particles of a gas compared to the size of the particles themselves. So we have the size of these particles right here, which is really much too large for the relative or average space between them, as shown in this diagram. However, in order to make a realistic diagram, an understandable diagram, we have to draw it like this, but it's really not the case when we think about it. Lastly, the speed of these particles, since they're a collection of particles in constant motion, the speed of the particles increases with increasing temperature. So the sample of the gas, if we have the sample of the same gas at lower temperature and higher temperature, the one at higher temperature, the particles will be moving on the average with a much greater velocity. This diagram here really shows how different the particulate makeup is between a sample of a representative liquid and a sample of a gas. Now here we have on the left we have a sample of liquid water. On the right we have a sample of gaseous water, which they write as steam. Perhaps water vapor would be a more accurate determination of that. However, if we took a sample, a very minuscule sample of any within any portion of that liquid water sample or that liquid sample, we would always have approximately the same number of particles in this particular sample. They're saying it's about 100, meaning that throughout that liquid we always have the same number of particles, because it's the same volume and all of the particles are in constant contact. Let's contrast this with the sample, the representative sample of a gas here over on the right-hand side. Really, if we take these little snapshots or areas and we inspect them, or if we could inspect them, we would find that virtually always we end up with completely empty space. Completely empty space on almost every area we sample. Every now and then we might come up with a sample which has one gas particle within it. And this really is telling, because basically it says that a sample of a gas is almost completely empty space. The air we breathe, when we think about it on the particulate level, is almost completely empty space with respect to the amount of matter in it. So when we think of a sample of matter, specifically a sample of a gas, we can imagine a number of ways that we can measure that. And I call these measurables. This term measurable is probably not in the dictionary, at least not in the way that I use it. But in any sample of matter, we can measure its volume, perhaps, or we can measure its temperature if we want. And now, I want to introduce, when we're talking about it specifically a sample of a gas, we have another measurable which, for whatever reason, is only used most of the time with gases, and that would be with respect to the pressure of the gas. Notice volume, temperature, and pressure. We're going to be looking at these with respect to their abbreviatory first letters, V for volume, T for temperature, and P for pressure once we get into what are called gas laws. But P, V, and T are the three measurables for a gas. So let's talk for a moment about what gas pressure actually is. In the diagram we see here, we see a representation of a closed sample of a gas, and our particles are indeed moving along very quickly, and they are not in contact with one another. Now notice that every once in a while, or more than every once in a while, these particles impinge on the surface or the inside surface of the container which is holding them, bouncing off, sort of releasing a force, if you will, into the walls of that thing that is holding onto the sample of a gas. So when we have a particle impinging off of a surface, that releases a force onto that surface. And the collective force of all of these particles pushing or impinging against these the surfaces of this container produce an average outward force. An average force. So that is basically known as the pressure of a gas. If there were no gas in there to create these impingements on the inside surfaces of the container, there would be a vacuum in there. And the outside air pressure, the particles impinging on the outside now of the container would be pushing in, trying to destroy that vacuum. So if we had to put a definition to the idea of gas pressure, sort of the way I just described it in the previous slide, it would be the result of constant collisions between particles in a gas sample averaged over the surfaces around them. Now here in this example right here, we could think of a pressure as a high pressure or a low pressure. One of the ways of doing that is if we have two separate containers, but they are of the same volume, and we have one with a greater number of gas particles in it and one with a less number of gas particles in it. Well, the one with the greater number of gas particles in it, it creates a higher pressure because there's more gas particles at any given time impinging off the inside surface of that container, whereas the gas sample with less particles in it is going to have a lower pressure because at any given moment there are less particles on the average impinging on the inside of that container. As with any measurement in any dimension, along with the numerical component, we have to have a unit of measure. And now that we're introducing this concept of pressure for a gas, we have to be able to define units of measure that will be going with a numerical component to that measurement. There's a lot of types of units of measure for gas pressure. As in this table here, we show here 6 of them. That is not the entirety of them, but of this 6 that are shown here, we use 3 of them most of the time, as you'll see. Those are atmospheres, which is abbreviated as ATM, millimeters of mercury, like in a barometer, which is given abbreviatorily that way, or torr. Those are the 3 big ones that we ultimately use. And in order to put out a number for pressure, we have to have a standard, that yardstick that we're going to compare all of them to. And that yardstick is considered the average air pressure at sea level. Average air pressure at sea level. Now, obviously, there's different air pressures in different areas of the world at sea level, very different variations, but so this would be considered the average. And if we use that as our standard, our three big ones that we're going to be using here, for instance, atmospheres, is so 1 atmosphere is the average air pressure at sea level. Millimeters of mercury, well, that's 760 millimeters of mercury is the average air pressure at sea level. For torr, which is the third one that we use a lot, it's the exact same size of the unit of measure. 760 torr is the average air pressure at sea level. So what we have here, and we don't have to just use these three ones that we're using, we could use all 6 of these or even more, is when we're presented with a table like this, we are actually ready to put together per expressions. Indeed, we could think of per expressions right from this chart. 1 atmosphere per 760 millimeters of mercury, or its reciprocal. 760 torr per 760 millimeters of mercury, or 760 torr per 1 atmosphere, and the list goes on and on. But I think you get my gist here, that ultimately, when presented with something like this, in this case, the average air pressure at sea level, it is a ripe environment for coming up with per expressions. And indeed, we'll be using these per expressions in dimensional analyses once we start talking about gas laws and how these the three measurables of pressure, volume, and temperature work together in a sample of gas. So having gone through some descriptive terminology with respect to gases, now we enter into the more calculational bent, and that's going to follow us through the rest of this chapter. So here we have, we're going to introduce what are called simple gas laws. Simple gas laws are essentially ways of putting together pressure, volume, and temperature, those three measurables of a gas, from an initial set of conditions and finding out an unknown one of these measurables in a final set of conditions. So simple gas laws have that first attribute. They all require an initial set of conditions, pressure, volume, temperature perhaps, and a final set of conditions, another pressure, volume, and temperature, once that gas sample has been manipulated in a certain way. Now, in most of our simple gas laws, most of them hold at least one of our three measurables constant, while the others are allowed to fluctuate. So for instance, temperature being held constant while pressure and volume fluctuate, or pressure being held constant when volume and temperature are fluctuated. Ultimately, these attributes, we will find, can ultimately be drawbacks, because it limits our ability to, as we'll see, to look at one of these changes going from an initial to a final set of conditions, to really look at the gas sample as a whole. So there are 4 simple gas laws that we'll be taking a look at, all of which have these 2 types of attributes. The first one is known as Boyle's law, then Charles' law, the combined gas law, and Avogadro's law. So we'll take a look at these one at a time, and we'll start with Boyle's law. All 4 of our simple gas laws have equations associated with them. If these equations are available to us, all that really requires is looking over a word problem, an example which we'll show coming forth, and plugging in the numbers. And there's always going to be one unknown, which we're going to solve for. So Boyle's law, whose equation is given right here, is essentially the relationship between the volume and pressure of a gas sample. And it has to be an enclosed gas sample, all of these do, while the temperature is assumed to be held constant. the equation given as P1V1 equals P2V2. Essentially, anything with the subscript 1 means our initial set of conditions, and anything with the subscript 2 means our final set of conditions. So let's take a look at what this ultimately means. Where if temperature is held constant in an enclosed gas sample, how do we fluctuate volume and temperature and keep that gas sample enclosed? Well, it's helpful to imagine perhaps a cylinder which is closed at the bottom of one end and open at the top. And into this cylinder, we put a piston. We put a piston that we see on here, and that piston is somewhat lubricated in order that it slides within that cylinder. So as we can see in here, we have this cylinder set up with a sample of gas inside, and whether that piston goes up or down, the gas sample stays within there. It does not escape. So here we have this piston, and we have a pressure gauge sort of welded into the side of our piston, and we can put weights or masses of varying size on top of that piston. Obviously, a heavier mass on that is going to compress that gas more, and a lighter one is not going to compress the gas sample as much. Now, gases, by the way, they are such that since we have our particles not in constant contact with one another, they're the only physical state that is readily compressible, because we can put those particles closer in towards one another quite easily. Now, solids and liquids, since their particles are always in constant contact, they resist being compressed. Although they can be compressed very, very little, we consider the fact that, at least in this class, that solids and liquids can't be compressed, but gas samples can. So in any event, we can see here that as the volume decreases, the pressure increases, as we saw before, because there's the same number of particles in there, but it's a smaller volume, so you have more impingements of those particles against the sides of the container. So this is known as an inverse relationship. An inverse relationship essentially says of these two measurables, when one goes down, the other goes up. And when the other one goes down, the other one goes up. That's given in a chart, which we see right here. Our inverse relationship between our initial and final observation of that gas is Boyle's law. So how do we work with this? Well, we are presented with a word problem, and let's take a look at that. Here's an example. A cylinder with a movable piston plug, just like we saw before, contains a gas sample with an initial pressure of 4 atmospheres and a volume of 6 liters. If the pressure is then decreased to 1 atmosphere, what would the resulting volume be? Notice all of those instructions involve just an initial pressure and volume and a final pressure and volume, and it always says assume constant temperature. That is a dead giveaway. We're working with Boyle's law, because Boyle's law is the only one that has a constant temperature, where T is held constant. So really, we're just plugging things in. We have our 2 initial sets of conditions. We have our initial pressure at 4 atmospheres and our initial volume at 6 liters. So we're just going to put those in there, P1 times V1. And then we look towards the other side. And in this case, if the pressure is decreased to 1 atmosphere, that's P2, what would the resulting volume be? That's the question. So that is our unknown. So we put those over on the other side. 1 atmosphere times our unknown V2. That is what we want to find. And once we set this up, and these, by the way, these types of equations in all of our gas laws are called plug and chug, or I call them plug and chug, because they don't require a whole lot of thought like a dimensional analysis would. These simple gas laws, we're just plugging in numbers and off we go. So once we work through this algebraically on our calculator, the final volume ends up being 24 liters. So our second simple gas law is known as Charles' law. It is the relationship between volume and temperature in an enclosed gas sample while pressure is being held constant. Pressure is held constant, so that term P is not in there. We only see V's and T's, that's volumes and temperatures. Of course, again, we need an initial and a final set of conditions. That's given by the subscripts 1 and 2 in there. And this is set up differently than Boyle's law, where in this case, we now have a sort of a numerator-denominator system. So let's look at how we could, what could we imagine as a vessel for holding this gas sample in which the pressure would always remain constant, but we could change the volume and or the temperature. And interestingly, it turns out that that particular vessel containing the gas would simply be a balloon. Now, interestingly, a balloon, whether you blow up a balloon to a very small size or to a larger size, the pressure within there is approximately the same. It would seem to be counterintuitive, but it is. Whether on a small balloon or the same type of balloon, blow it up a little larger, the pressure is about the same. And that's because of the flexibility of the borders, the boundaries of this the vehicle that the gas sample is held in. So if we have a balloon and we fill it with a sample of gas, it makes sense that the hotter that sample is, it will expand. And the cooler that sample is, it will contract. We saw that before, this idea of contraction and expansion. So for instance, if we took our balloon with a gas sample and we put it in ice water, which is at 0 degrees Celsius, and then we took it out and we placed it in boiling water. It would probably have to be a very sturdy balloon, so it wouldn't melt from the boiling water. But if it did hold together, then that gas sample would expand. It would expand, and the pressure going from one to the other would stay the same. Now, Charles' law is considered as a direct relationship between volume and temperature, meaning as one goes up, the other goes up directly. As one goes down, the other goes down. That's different than Boyle's law, where we had the inverse relationship, where one goes up and one goes down. So that we have this ultimately gives a straight line on a graph if we were to measure the relationship between volume and temperature in a gas sample. Now, temperature is going to have some idiosyncrasies to it that we're going to look at in the next slide when we look at a particular example. So let's do that. So here's Charles' law, and here is an example problem. A sample of a gas has a volume of 2.8 liters. Okay, that would be an initial volume, V1, at 2.8 liters at an unknown temperature. Oh, T1 is unknown. That's what we're solving for. If the sample is cooled to 0 degrees Celsius, okay, that is temperature 2, T2, and its volume decreases to 2.57 liters, that's V2. What was its initial temperature? And assume constant pressure. Again, a dead giveaway for Charles' law. It's the only one that holds pressure constant. So here's a salient feature with respect to temperatures. In any gas law, we're going to be looking at least 4 of them in this lecture and others when we go into the next lecture. In any gas law, when we have temperature, that temperature must always be in kelvins. If it is not in kelvins in the problem, we have to convert it to kelvins in the problem. Always, any gas law, the temperature must be in kelvins. If you don't put it into kelvins, it will not work out properly. So in this case, we do have a temperature but in this example problem, but it is in degrees Celsius, 0 degrees Celsius. So we need to convert that to kelvins before we can plug into Charles' law. That's a classic mistake made by many students before. So always remember, any gas law that has a temperature, just convert it to kelvins, and we'll be off. So now that we've converted 0 degrees plus 273 to 273, we can plug in our numbers of V1, V2, and T2, and ultimately solve for T1. So down here is our initial volume and an unknown initial temperature. So we have that. Then we put on the other side our final volume and final temperature in kelvins. And at this point, it just becomes elementary. We take out our calculator and off we go. And we find that T1 is in kelvins, 297 K. That is T1. If the question should say, what is its initial temperature in degrees Celsius? Well, then you'd have to calculate back calculate that, subtracting 273, and it comes out to 24.4 degrees Celsius. So sometimes we have a word problem, an example where all three gas characteristics, all the measurables, pressure, volume, and temperature, do fluctuate. It is possible to do that. It gets us out of the framework of Boyle's law and or Charles' law, because they have to hold at least one of those measurables constant, but that's not always the case. When that is the case, when we have all three gas characteristics fluctuating, we can end up using the combined gas law. Combined gas law, because it combines ultimately Boyle's law, if you look pressure and volume in an inverse relationship, and Charles' law, volume and temperature in a direct relationship. It really puts them together, which is fine, but we have to be able to recognize from a potential example problem that, well, there's nothing held constant, therefore I'm going to be using the combined gas law. There's 6 variables in here. Obviously, 5 will somehow be given to you. You're going to solve for the 6th, but I suggest caution in these, because plugging this many things into one equation can ultimately end up being problematic. It can make it easier to make mistakes. So, as I said before, this illustrates an inverse relationship with pressure and volume and a direct relationship with volume and temperature, this combination of Boyle's and Charles' law, which is the combined gas law. So, pressure and volume, as always in these simple gas laws, can be of any unit of measure. Pressure can be in atmospheres, can be in millimeters of mercury, and torr, it doesn't matter. As long as they're the same on either side, it doesn't matter. The same can be said for volume. Volume could be given in milliliters. Volume could be given in liters or gallons or whatever. That's fine, as long as it's the same on both sides. Always, again, temperature must always be in kelvins. Let's take a look. Here's an example. A gas sample has an initial volume, V1, of 158 milliliters at a pressure of 735 millimeters of mercury, that's P1, and a temperature of 34 degrees Celsius, that's T1. If the gas sample is compressed to a volume of 108 milliliters, that's V2, and a temperature of 85 degrees, that's T2, what is its final pressure? So we are solving for, as we'll see, P2. We're going to solve this for P2, and we notice that everything is fluctuating, so we're going to use the combined gas law. And really, it's just a matter of plugging in numbers here. You got to be careful plugging them in and carrying out the calculation on your calculator, but it's just plugging in numbers. First thing we, of course, have to do is, lest we forget, we have to convert both of our temperatures to kelvins. Before we even start to proceed, we have our 2 Kelvin temperatures just by adding 273 to each of these, and then we can just plug these numbers in. On the initial side, we have P1, V1, and T1, and then on the final situation, we have P2, which is our unknown, 108 milliliters for volume, 358 kelvins for temperature, and it's automatic at this point. P2 ends up being 1250 millimeters of mercury. That was what we were looking for. That is what we solved for. And the last one, our last simple gas law, that is known as Avogadro's law. Avogadro's law has an important component to it, more important than the ones that we've seen thus far. Pressure, volume, and temperature, or P, V, and T, the measurables I have been talking about, are exactly that. They are directly measurable within a gas sample. But Avogadro's law is the first time we bring in something that I consider an immeasurable, something that is not directly measurable. And that is the number of moles of a sample of a gas. A number of moles we cannot directly measure. We could directly measure a mass and then using a molar mass be able to calculate the moles of a sample. However, it is not directly measurable, and thus it has import and value to us. It is, and it's set up similarly to Charles' law. It's a direct relationship. The direct relationship between volume of a sample of gas and the number of moles within it. So we'd have to tailor which simple gas law we're going to be using to the question or the problem that's given to us. If we're talking about number of moles in this problem, chances are it could be in Avogadro's law. So we have volume and number of moles are directly proportional, meaning one goes up, the other goes up. One goes down, the other goes down. That makes sense. You know, if I have less number of moles of my sample, it's going to have less of a volume. And importantly, in this case, both pressure and temperature are assumed to remain constant. So let's look at an example. A 4.8 liter sample of gas contains 0.22 moles of that gas. How many additional moles of the gas must be added to the sample? Okay, so we're adding extra moles in to obtain a volume of 6.4 liters. So that's a greater number. So let's put this together. Now, the real giveaway here is assume constant temperature and pressure. You will never see that unless it is an Avogadro's law problem. So we are going to use Avogadro's law. And we'll notice that we have our initial volume and number of moles already set up. So we're going to put those right into Avogadro's law. 4.8 liters in the numerator, 0.22 moles in the denominator. Now, if you think about it, there really is, through Avogadro's law anyways, no way to directly measure how many additional moles of the gas we have to add. We can only come up with, using Avogadro's law, that final number of moles. And then we can subtract and find out how many additional moles of gas were added. So, final. So here we have the final volume, which we do indeed have, 6.4 liters. So we're going to be solving for that final number of moles of the gas. So we set this up this way in Avogadro's law, and we solve for N2. That is the final number of moles in that sample after some were added to it. Notice this isn't the answer. The answer is asking for how many more additional moles are added to it. So thus, we have to carry out a subtraction. The final number of moles minus the initial number of moles gives the number of moles of additional gas added to that sample using Avogadro's law. Full stop.